All right, our next one. Ooh, our next one is the really, really big one, the big open response one. So this is the one where students in a physics class are trying to study energy changes in objects they experience as they fall. They're going to drop a metal sphere that has a mass of 0.05 kg from a height of 20 meters. So those two things are important for us to remember. These right here is everything that they're predicting. They predicted these results. And we want to know first, using predicted speed, calculate kinetic energy at 2 seconds. So here, let's pause and go over and do that. So let's see. First off, kinetic energy is half the mass times velocity squared. So our mass is right there. So half of 0.05 is going to be 0.025 kg times, let me slide this over some. Well, what's the speed at 0, or 20 seconds, right here, because that's our speed. 20. So times 20, nope, that's not the pen, this is the pen. 20 meters per second squared. All right, that's going to equate to 400 meters squared per second squared times 0.025 kg. Do that math and you're going to get a resultant of 10 joules of kinetic energy. So that is our answer to A, 10 joules with units. All right, B, using the predicted values, let's calculate the gravitational potential energy at 0 seconds. So here, we need to get gravitational potential energy. Remember that gravitational potential energy, P, let's get the pen again, PE is mass times gravity times height. So our mass, which again, we got from, let's slide over, so we got it again, we've got it right here, right there. 0.05, okay, so we've got 0.05 kg times gravity, which is 10 newtons of force per every kilogram of mass, times height, which, well, what is it at 0 seconds? 0 seconds, it's at a height of 20. All right, so let's plug that in. 20 meters. Notice our kgs cancel out. You're left with Newton meters, which is joules. Do all the math, and you'll find out the answer is 10 joules. And take a look at that. Kinetic energy at the bottom, potential energy at the top. Now, doesn't that make sense? Cool. So, let's go back and look at our last two parts of it. Describe what happens, right here, to the gravitational potential energy and the kinetic energy as the sphere falls. Well, we know this. That's simple. As a sphere falls and goes down, potential energy turns into kinetic energy. That's it. It's that easy. And after the sphere is dropped, we find out that the results of the experiment are slightly different than we expected or predicted. What's one reason for that? Well, what's one thing that we always neglect? Friction. We always neglect friction. Every time, no matter what. In this instance, it's called air resistance. So we're neglecting air resistance. So that's our answer to that. Now on the MCAS, you would be expected to flesh these out into nice, big, long sentences. So don't do it as small and as easy as what I just did right there. Explain fully. Moving on. Ooh, I had a lot of blank space there for extra work if necessary. All right, four students of different weights timed themselves walking up a set of stairs. Their data is shown below. Which student used the most power while walking up the stairs? Well, that's pretty straightforward. Let's first remember that work is force times distance, and power is work over time. So our force is the weight, our distance is height, and we can figure out work. And then to figure out power, we just have to divide by time. So it becomes as easy as 440 times 4 divided by 15.5. So our first student, 440 times 4, is 1,760 joules of work divided by 15.5 seconds is equal to 113.5 watts of power. Do the rest, 550 times 4 divided by 220, and so on and so on. If you do that for all of the other ones, you're going to find out that student W actually has the biggest amount. And I'll let you guys do the other ones to confirm, but to give them to you, student X, 550 times 4 divided by 220 nets us 100 watts. Student Y, 410 times 4 divided by 15.8 nets us 103.8 watts. And then student Z, 575 times 4 divided by 23 is also 100 watts. So student W is our winner. Most power done. Remember, work is transfer of energy. Power is rate at which you complete work. All right, let's move on to our next one. The table below provides information about the daily use of some typical appliances. Which appliance uses the most energy? Well, if you first remember that work is all about transfer of energy from one thing to the next, and you know that work is represented in units joules, and energy is represented in units of joules, you can figure out that if you know work, you know the energy. So let's see what we have. We have power in watts and duration of use in hours. So this is power, this is time, that's what those columns represent. And I will say it's important to understand that 1 watt is equal to 1 joule of energy consumed in 1 second. So notice up here that we don't have seconds, we have hours. So if you were asked to find out the work done by each of these appliances, you would need to convert all of these times into seconds. But because we just want to figure out energy and we're doing a understanding of a relationship, you can ignore that, but only for this. So we want to know work. And remember, power is work over time. So if we want the work, we need to multiply by time, and work equals power times time. So we just need to multiply all of these by one another. So 1,500 times 0.5 is going to get us 750. 1,000 times 1 is 1,000. 50 times 12 is 600. And 1 times 24 is 24. So you can clearly see that our 1,000 winner has the most energy. So the answer is B, the air conditioner. A man applies a force of 100 newtons to a rock for 60 seconds. But the rock does not move. What is the amount of work? So we need to know work. Work is force times distance. Well, if the rock doesn't move, that means it moves a distance of 0 meters. And the force applied is 100 newtons. 100 times 0 is just 0 joules of work. So if nothing moves, no work is done. You actually don't have to do any math on that. But if you want to, I just did it to confirm it. This doesn't matter at all. You don't need that to calculate work. If you want to calculate power, then you would have to do it. But if you don't do any work, you don't do or have any power. So that's the answer, 0. All right. On to our next one. Let's just see, how many more of these do I have? I've got, oh, 2 more. That's it. All right. So, which of the following is the best example of work being done on an object? Well, let's see. Remember, work is force times distance. So you need both for work to be done. Also, remember that in order for work to be done, you need to apply force in the same direction of motion. So if this guy pushes an object that way, he's applying force to the right, it's moving to the right, work is done. But if this same guy was carrying this in that direction, in order to carry something, he has to apply force up. But distance is to the side. In this instance, work is not done. So let's see. Holding a 50-kilogram barbell. Nope. If you're holding something, it's not moving any distance, no work. Lifting a bag of groceries. Well, if you lift a bag of groceries up off the floor, you had to lift up, it moves up, it's same direction, so work does get done here, but let's just check the other two. Keeping a board in place, the board's not moving. Pushing in a car that won't move, oh man, all of these aren't moving. There's no distance in any of these. That one's easy. B, lifting a bag of groceries is the best example of work being done. All right, on to our last one. In a competition, weightlifter 1 lifts a 100-kilogram weight from the floor. So, all right, we've got weightlifter number 1 right here. We'll say this is guy number 1, and he's lifted this 100-kilogram weight to a certain height. Cool. Weightlifter number 2, we'll make weightlifter number 2 blue, also lifts a 100-kilogram weight. Okay, so also lifts a 100-kilogram weight to the same height. Oh. All right, well, that's simple. But takes longer to do it. Okay, so this guy is slow. All right, which of the following statements describes work done and power used by the weightlifters? Well, before we even look at it, let's see this. Let's notice that they both lift the same exact mass, the same exact distance. So for work, if work is force and distance, if the mass was the same, force is based off weight, they have the same weight, same. And if they went the same height, this is the same. Therefore, they must have done the same work. So let's look up here. Weightlifter 2 does the same work. Yes, could be that. Weightlifter 2 does less work. No, can't be B. Weightlifter 2 does the same work. Okay, it could be that. Weightlifter 2 does more work. No, it can't be that. So it's either A or C. What about power, though? Think back to when we were walking up the stairs. Think about me. Remember, I did the most work because I weigh the most. But remember how I was the least powerful? How slow was I moving up the stairs? Really slow. Remember, power is all about how quickly you can use work. So if they have the same work, a slower person is going to have less power. So less power, not more power. Our answer is A. Weightlifter 2 does the same work, but is less powerful.